No questions? It's too easy a class. Okay. Yeah.
Okay, sorry, I have on the diffusion bonding, the TLP diffusion bonding.
Yep.
How does the strength of that bond compare to regular diffusion bonding? The same, less?
It depends. A true diffusion bond has nothing else other than just the two base materials, and if you don't get too large a grain size and you don't get porosity at the interface, you make a pore-free, equal grain size joint. You can't tell the difference. Now, you can only do that in certain materials. I mean, aluminum, magnesium, you always have this little layer of oxide, and so maybe it's not perforated with porosity, but it's perforated with oxide. But titanium, you can make a perfect bond. If you go to TLP, you've got another element in there. You've got the melting point depressant. In nickel boron alloys, it's the boron, and the boron can lower the strength. It doesn't have to, and if you diffuse it away far enough, it doesn't lower it at all. So it really depends on the specific metallurgical system. But generally, it's stronger than a braze generally. It's definitely stronger than a solder joint. Whether it's equal to a weld or not really kind of gets to be a question of what's the metallurgy of the specific alloy system. Now, when I first started talking about this stuff in the mid-'80s in a graduate course like this, I used to basically say, well, it's really sort of specialized in nickel-based alloys. Because back then, that's about all we ever thought about it, okay? It was TLP defined as a terminology trademarked by Pratt & Whitney. And I mean, that had only come out in the paper 12 years before, and it takes time for people to realize what's going on. Well, it turns out, I was just looking this morning at a book, and I actually had a student work on doing, I mentioned low temperature TLP, where we're basically, people bond a gold chip, a silicon chip, to its substrate when they really need good thermal conductivity. Well, let me back up, since I was going to talk about soldering today anyway. But what they call die attach, I'm going to turn this into a long-winded answer. What they call die attach is I've got the silicon chip, and I want to bond it to this aluminum oxide chip carrier. And it's got about 6% manganese oxide in it, typically. That's why it looks black. And I want to bond that. Well, the simplest way to bond that is just with an adhesive. So the first thing is adhesive, but typically silver powder filled. These things operate, I mean, we're now at 2 and 3 gigahertz and pushing towards 4 gigahertz. These things need a ground plane on the backside, or they run into all kinds of problems. I'm going to run into problems if I don't switch this. It's on the wrong receptacle. But in any case, so they typically use an adhesive that has a silver powder in it, and the silver powder gives good thermal conductivity. It also provides a ground plane to the metal to the substrate. Now, virtually all of these chips nowadays at these high frequencies, when you're getting into the 500 megahertz and stuff above, the silicon actually has a layer of gold on the backside. They metallized it, they vapor deposited a thin layer of gold as the ground plane on the backside. And in fact, I used to have one of those things that hadn't been bonded yet, and you'd see the silicon wafer on that side, one side. Actually, I didn't bring them. The Pentiums already, I'll try to remember to bring one tomorrow. But the Pentiums I passed around actually had gold on the backside. You can see the chip on one side with the circuits. You flip it over, it's just a gold coating. So when people need something better, they'll use tin in here, and they'll form a gold tin. Actually, there's 2 different gold tins, I think, if I remember correctly. They'll form gold tin intermetallics, and that gold tin intermetallic melts at around 320 degrees centigrade or something. But remember, 300 degrees centigrade temperature rise, and you get yield level residual stresses, so you have to have a substrate that matches the coefficient of expansion of the ceramic. you have to have a ceramic that matches the coefficient of expansion of the silicon. And so you can't just use straight Al2O3 with manganese oxide. You usually have to use something like nowadays the fancy thing is an aluminum metal matrix composite. It's basically silicon carbide at about 60 volume percent infiltrated with aluminum. So it's an aluminum metal matrix composite, and it matches the coefficient of expansion very, very closely. And so you don't have a problem of breaking the chip from thermal expansion stresses. But this is basically, you could talk about this being a diffusion bond or a diffusion solder joint, where all I've done is I've diffused the tin into it, but I formed an intermetallic. But the problem is the intermetallic's a little bit brittle. And so people have tried a number of other things, but I was just looking this morning in this book, which is a 2004 book, Principles of Soldering. I guess there was a 1993 edition, but they actually talk about here diffusion soldering. This thing down a little bit, okay? Diffusion soldering, and if I zoom in on this guy, this table, selected diffusion soldering systems, copper indium, copper tin, and it talks about the process temperature is 180, the remelt temperature is greater than 307 degrees centigrade. So they're actually forming a low temperature transient liquid phase diffusion bond. Back when we published this in the early 90s, we called it low temperature TLP. They call it diffusion bonding. And lo and behold, this is their little schematic of how the process works. It's not all that different than the schematic that I showed you of diffusion bonding. Well, in fact, where did they steal that from? They kind of took that out of the old welding handbook and adapted it for soldering, where you basically put in this case, they say metallization, a preformed inner layer. The inner layer melts, isothermally solidifies, a heterogeneous bond. If you hold it there long enough, you get a homogeneous bond. Well, in this case, this is a TLP joint, but it doesn't have the properties of the material on either side because it's still, it says homogenization, but it's still a joint layer. And this is basically a solder joint. Over here, this is an intermetallic, so it doesn't have the same properties. So it does get into the specific metallurgy of the system that you're talking about, okay? So I just kind of jumped ahead to some of the things we were going to cover anyway. Since you asked the question, gave an answer. I actually would prefer to just kind of not lecture, but have you ask questions and let me fill in, what I was going to talk about anyway in response to your questions. But that's okay. If you don't have the questions, then I'll put things forward. Since I didn't get in here in time to write things on the board, some of the things we talked about last time, diffusion bonding is limited on the low side of the temperature range. Remember, 6/10 to 8/10 the melting temperature typically, by slow kinetics, and on the high side by grain growth. This is not transient liquid phase. This is just the regular old diffusion bonding. And TLP bonding, on the other hand, starts out as a braise, or in this case, the one I just showed, as a solder. I mean, if I went back 20 years ago, I didn't talk about TLP in anything other than braising and high temperature nickel-based alloys. But we now recognize that it actually occurs in soldering, and it's been occurring for hundreds of years, if not thousands of years. In fact, part of the story that I didn't tell you, well, I'll get to that in a second if I can remember it. Let me finish up. TLP starts out as a braise and ends up as a diffusion bond as you diffuse away the melting point depressant. In some cases, it can be boron in the case of nickel alloys. It can be silicon in the case of nickel-based alloys, but it's going to be a very slow process because silicon is a substitutional diffuser, not an interstitial diffuser, and therefore it diffuses a lot slower because it has defined vacancies. An interstitial diffuser has always got interstices in the lattice, and so the diffusion is about 1,000 times faster. TLP reduces the pressure and time required for the bonding, and the reason it does that is I don't have to have as close a fit up because I'm going to impose an inner layer. I get liquid phase diffusion, which is many orders of magnitude faster than solid state diffusion. And I also get a liquid in there that can help dissolve away some of the impurities, the oxides and stuff, in certain cases. So I can make bonds with less pressure, less fixturing, less time. It's just a much better process. Well, let's now wanted to tell you. Well, let me back up. So the thing I almost said I was a second ago. I told you about the Etruscans were using it back in 600 BC to put these little gold beads on copper vases and stuff. And people actually have cut through these vases and stuff, and they've looked at them, and I can't remember if they were using tin or whatever, but they were basically getting a TLP type of bond. If you go do the metallurgy on it now, there's no solder left, okay? It's basically a diffusion bond, but it's a TLP bond because they basically soldered the beads on and then diffused them away. So the Etruscans were doing it, you know, same thing Pratt & Whitney was doing, but in 600 BC. And people think, remember King Tut, the 2500 BC, the Egyptian prince or king, you know, they have the famous Egyptian mask and his beard and stuff. They think that King Tut's dagger was also TLP bonded, but no one wants to cut it open to make sure. I mean, some people have no interest in science, okay? But they haven't, you can't tell very easily. Actually, you might be able to do neutron diffraction on it or something nowadays, but you know, you just have to get someone who wants to spend the time to prove whether it's TLP. So the Egyptians may have used it 2500 BC. I figured since we got a majority of people in here who are in the Navy, I'd tell two Navy stories from the New England area that relate to TLP. One is a story where a company up here on the North Shore was building what's called a cross-field amplifier. A cross-field amplifier is a way to magnify microwaves for radar and things. And if you're a pilot, you don't like to fly way up here where people can you know, get you with their radar. You like to fly low and kind of hug the earth and be like a race car driver ready to run into the wall at any time. In this case, the mountain at any time, right? And so these folks were building a cross-field amplifier is nothing more than a bunch of fingers of metal with high voltage on them, and you pulse an electron beam through there. But you modulate the electron beam with the microwaves and you modulate the fingers with the microwave voltages, and when the electron beam comes through there, it gets modulated by the electric field. It's cross field because the electron beam's going this way and the fingers are going this way, and they make a cross, okay? It's cross field amplifier, so it sort of works in the same way like a transistor does. In the transistor, you put a little bit base current in, and you multiply the power coming the other way down, right, through the transistor. Well, in this case, you modulate these metal fingers, and you put a high power pulse of an electron beam through there, and that modulates the electron beam and magnifies the microwaves, okay? Well, it turns out, and this was basically going into these Navy aircraft and for ground hugging as you're going along at, you know, Mach 1 at 300 meters over the ground or something, so you avoid people's radar and stuff. And they had been brazing, well, they had to braze a molybdenum tip on the end of a copper finger. And the reason, so basically the cross-field amplifier had a cross-section look like this, and this was copper. There's another one over here, looks the same. Actually, the whole thing was actually symmetric. There's a whole bunch of these going around 360 degrees. And on the end of this, you want to put some molybdenum. And the reason is the electron beam is going to come through this little hole right through the center, and you're going to modulate this with the microwave signal that you got, and you want to magnify it with the electron beam coming through. So you pulse this electron beam through here. There's so much power in the electron beam that it can melt the tips of the copper. So you put something that's very, very refractory, molybdenum melts at like 2,500 degrees centigrade. You want copper to carry the heat away, because this thing, when you pulse that electron beam, you're going to just kind of flash heat that thing. You don't want it to melt, because if it melts, then you change the electric field around here. And if you change the electric field, you're not going to get the right thing amplified. So they had been brazing this with an 82 gold, 18 nickel braze alloy. And it turns out they were having, well, they actually hadn't had problems. They had had one or two where one of these little tips had come off, and that screws up the whole thing. And your radar doesn't work. And you go flying into the mountain at Mach whatever. Okay? So they were trying to come up with something better. And this obviously is also a fairly expensive braze alloy. It's 41% gold, right? I mean, it's not 40, it's 82% gold. I'm thinking of another thing, another case where they were brazing some parts. Maybe I'll bring in one of those parts. And they used to have this stuff in 50-ounce bottles. Okay, a 50-ounce bottle of this braze alloy had 41 ounces of gold in it. Okay, that's what I was thinking of. But anyway. So they were using this, but the problem is molybdenum and nickel form an intermetallic, which is brittle. And I talked to you about the problem in diffusion bonding is if you form brittle intermetallics, you end up with a lousy joint. And so they determined that was part of the problem, so they switched to a different braze alloy. And the braze alloy, well, actually, let me back up. What they did to me is they sandbagged me as a consultant. They brought me in and they said, well, we got this problem. And they explained it to me. There's like 10 people in the room. And I said, boy, they said, how can we get rid of this brittle intermetallic? I said, well, you know what you really want is you really want a transit liquid phase diffusion bond in something that doesn't form a nickel-3 molybdenum intermetallic. You don't even want any braze alloy in there. You want something that's going to be a diffusion bond, and you could make that by TLP. They said, well, how do we do that? I said, well, I don't know. I'd have to develop a braze alloy that wouldn't have that. And they said, after about 2 hours of discussion, they said, well, we actually found something that seems to work pretty well. And it turns out this particular one, if you took the part and you bent it, you could get like 2-degree bend angle on that molybdenum and copper before the thing would just snap. No real ductility at all. And they showed me a piece with this new braze alloy that they had bent like 90 degrees and the copper had just stretched. No brittle intermetallic, wonderful joint. The molybdenum is much harder, so the molybdenum hadn't deformed, but the copper had just, being a nice soft ductile metal, had just deformed tremendously. So this thing would take tremendous stuff. And they said, well, we tried a braze alloy, and it turns out it was 37 gold, and it was 3% nickel, and it was 60% copper. And we got these great properties, and we're trying to sell this to the Navy, but they think we're just trying to lower the cost of the braze alloy. And this is such a critical thing that they won't buy off on it. And I said, well, I don't know what you got, but I'll go look at it. So I give it to one of my, give it a sample to my graduate student to do metallography and polish it. And he comes back and he says, I can't find the braze. And I go and I look at it, and I realize they had developed a TLP joint. They didn't know it, okay? They thought they were just using a different braze alloy with less nickel. It turns out they did get rid of the nickel-3 molybdenum intermetallic, cause lower nickel, lower the activity of the molybdenum, and you didn't form nickel-3 molybdenum intermetallic. So they got rid of the intermetallic, but it turns out the gold and copper, or the gold just diffused into the copper as the melting point depressant, and they ended up forming a TLP bond. And they didn't know they had stumbled on it. And I ended up writing a letter explaining all this, and the Navy internal person at the site signed off on it. Another story that has to do with TLP was Raytheon, this is about 15 years ago or so, Raytheon had soldered together 3 transformers that were transformers that controlled the control rods for a nuclear reactor and a nuclear submarine. And these were $500,000 transformers. Okay, I don't know all the details of them, but they cost about $500,000 a piece. Well, it's nuclear, quality, and it's kind of specialized equipment. It's Navy equipment and everything. And in order to shield this, they had a piece of copper foil, copper sheet, that wrapped around the whole thing. And in order to make the electrical connection to this ground sheet, they basically just soldered a copper wire to that took that to ground. And what had happened is the whole thing, so I've got this transformer, it's got this, so the transformer's in here. This is a piece of copper sheet. I don't know, it's like 10,000 copper sheet. And they just had a little solder joint with a wire. And the solder was supposed to be 95 lead, 5% tin. and that melts at around 300 degrees centigrade. And the reason they wanted a high melting solder is this whole thing had to be burn in at 220 degrees centigrade, and regular lead tin solder melts at 183. And so you couldn't use regular lead tin solder. And so they made up 3 of these things. The whole thing gets potted together in this kind of plastic and everything. And then they have to put it in for this burnout or bake out, whatever you want to call it. It's basically a thermal stress test to make sure everything's okay. 24 hours at 220 degrees C. And I mean, I guess the top of the reactor can get some high temperatures in bad situations, and so they didn't want to lose the ability to move the control rods, and so this thing had to be able to take certain excursions, right? Well, when they were doing the bake out, this whole thing is in some sort of metal container. I mean, it's a pretty good sized transformer. I actually never even saw them, but apparently there's a little hole where one of the leads comes through, and they got this little puddle of solder during the 220 degree test, and it turns out they analyzed it. It was 60 tin 40 lead, which happens to be the eutectic, which melts at 183. And they went back and they checked through the processing records and found out that the technician who had soldered it together had used the wrong solder. The whole thing's now potted up. And the Navy says we can't buy this because, you know, the joint's going to come loose. I mean, they could tell the joint was good, and so they had $1.5 million worth of transformers that they were going to have to scrap, and they were going to be delayed in their, you know, getting it to the fleet and everything else. So they called me up, and I came in. They explained all this to me, and I said, "Oh, you don't have a problem. All you've got is a TLP joint." And they said, "What do you mean? What's that?" So I explained what TLP was. And they said, "Well, you know, we've done some tests. We actually took some afterwards, and we soldered them with the eutectic lead tin, and we stuck them in a furnace at 220. These were just test specimens, just copper sheets with wires on them. And then we did tensile tests, and we found they wouldn't remelt until they didn't fall apart until 300 degrees centigrade." I said, "Well, that's right, because the tin just diffused into the copper and left behind a rich lead inner layer right here." Okay? And it turns out that they had already done the test, and they knew that the thing was good, but they couldn't explain why, or they actually didn't know it was good. They thought it might be good, which is why they brought me in, but they couldn't explain why. And so I actually went back and wrote them a letter and attached a copy of this little TLP paper that you guys have got. This one, right? And that's all the Navy guy needed in the quality control. He just needed a name. Actually, he needed to know there was some science behind it, right? But, you know, you just need the little marketing name, TLP, that they had formed a TLP diffusion bond, and the Navy bought $1.5 million worth of transformers, got them on time. They didn't lose any money, and Raytheon made a lot more money than if they had scrapped them. And I made $700 as a consultant, if I remember. I got to figure out some way to get a higher percentage of the savings. You know? But anyway. And actually, on Friday, I was down with a guy who's an expert on fire sprinkler systems. And he was telling me he's done studies. Some fire sprinkler systems have to have a remelt temperature, and they basically, the triggering mechanism in the sprinkler in the ceiling in some places is basically just a solder joint. And they use a solder that melts at a particular temperature, and that's what controls the whole thing. It turns out he has a patent on using nickel rather than copper as the two metals that are brazed or soldered together for high temperature applications. Now the patent's expired, he got this years ago. But it turns out the problem is if you use copper, you can use it for the 160 degree systems. But if you for a 212 degree system, sprinkler system, if you use copper, the tin diffuses in over time. I mean, this thing could be 20 years old, and just at those temperatures over 20 years, you'll get enough diffusion that the melting point of your solder increases because you're getting rid of the melting point depressant, the tin. And so he uses nickel because nickel forms this nickel 310 intermetallic and slows down the diffusion. So, you know, there are other times where you do transit liquid phase diffusion bonding.
The filler method for the TLP, for the braising, are the same or I mean, generally different? Use the same.
in many cases, you can find a braze alloy. I mean, I always thought that the nickel boron braze there were nickel boron braze alloys for these jet engines, and someone just left it in the furnace too long. It's always been my theory, and they found out they ended up with a better joint by leaving it in the furnace too long. This case, these guys thought they were going to a different braze alloy, and in fact, they ended up with a TLP joint. Okay. In the case of this, they're using a regular solder alloy, and they ended up with a TLP joint. Many times you can find a commercial solder or braze alloy that if you leave it in the furnace long enough becomes a TLP joint. But sometimes you have to design your own, okay? You can't, but I would say more often than not, people figure out, more often than not, people don't even know they're forming a TLP joint, okay? In fact, most of the solder joints that we have, a lot of electronics will go through a 24-hour burn-in. After they build the whole circuit and everything, they'll put it in an oven and they'll just leave it at 180 degrees. A lot of times they're just strengthening the solder joints. And in fact, that was one of the things this guy, sprinkler system guy, has done studies on the sprinkler heads that come back after 10 or 20 years. And he's done studies and he shows that these things just get stronger and stronger over time. Why? Because you're getting rid of the melting point depression, you're getting out of the creep regime, you're raising, and not in those things necessarily, but the solder joints basically as they age get stronger and stronger. And I was surprised. I said, well, how much? 10 or 20%? He says, no, 300% increase in strength. Okay, in some cases. I told him he ought to publish it. So he emailed me over the weekend and said, well, he didn't think he might be interested. I said, I think people would be interested in 300% improvement, whether they can use it or not. I mean, when you got a diffusion bond joint as opposed to a solder joint's going to creep at slightly elevated temperatures. A diffusion bonded joint the neat thing about diffusion bonded solder joint is you can make the joint at very low temperatures and it won't remelt until very high temperatures. The student that was trying to do this die attach for me a few years ago with low temperature transient liquid phase, he was looking at gallium arsenide rather than silicon because gallium arsenide is a lot more brittle than silicon. He actually worked for Raytheon. And we wanted to bond at like 100 degrees C. And you can bond at 100 degrees C and the thing won't remelt until 300, 400, 500 degrees C. So you can make a low temperature joint and then you end up with a high temperature joint, okay, which is kind of a neat thing. However, there are times when you want to go the other way. I have a Japanese company is coming in at 11:30 to see me today because they basically make these nickel braze alloys for jet engines and land-based turbines and stuff, and they want to repair these things, and so they want to undo the joint. Well, I got this request about a week and a half ago through the MIT Industrial Liaison Program, okay, and these companies kind of join MIT and they get free advice from faculty if the faculty are willing to sit down with them. And I said, well, tell me what the metal system is, your kind of question earlier. If I don't know what the metal system is, I can't tell you much about it because they get very specific. Well, it turns out I get the email back last week, oh, we're interested in nickel-based alloys. Well, I know the Japanese company, and I know they make land-based and air turbines, aircraft engine turbines. And they basically want a way to unbraze what are probably, I'm going to find out, are just more specific, are probably nickel boron joints. Well, how do I unbraze a diffusion bond? Okay, so I got to give them advice on how to do that because they've been trying to do it and haven't been able to do it. Well, they're bright people, and they haven't been able to do it. So I'm supposed to tell them. They're smarter than I am. So, however, what you do in something like that is, actually, I'll tell you. You want to know how you do something like that? You go back to the fundamentals. Okay. And when I first read that, I thought, oh, gee, this can't be done. And that's usually kind of my initial reaction or something. But then as you stop to think about it, and you think about it as you're walking to get a drink of water somewhere, or driving home in the car, or in the restroom or something like that, and you think about these things. I mean, maybe you think about other things, but this is what I think about. Someone asked me a question, and I want to solve the problem. And it turns out, difference nowadays between a nickel alloy and a nickel boron alloy. There are computer programs that will do that. And so if I know what their alloys are, I'm going to tell them, Well, have you bothered to calculate the chemical potential difference? Because there may not be enough chemical potential difference that you're going to be able to do this by any chemical technique. They're thinking in terms, I know already from the inquiries, they're thinking in terms of a chemical dissolution technique, okay? And they want to use a chemical difference to unbraze it. I mean, you can't just heat it up, or I'm sure they've tried to heat it up. A lot of solder, you want to unsolder something, you want to unbraze something, you heat it up back to its melting point, and you pull it apart, if you're lucky, if it hasn't formed a TLP joint. But in an engine that's been running for tens of thousands of hours, likelihood is it formed a TLP joint, you now have a diffusion bond, and if you're going to eat that way chemically, the chemical is going to have to eat it away based on a chemical potential difference. Okay? If there's no chemical potential difference, nothing that you're going to put on there is going to attack it. There's got to be a difference in energy between the braze and the base metal, right? And there's probably not much of a difference if you start looking at these things. There's certainly not going to be much of a difference in melting temperature, and there may not be much of a difference in chemical potential. If there's no difference in chemical potential, there's no way to dissolve it chemically. So how do you do it then? Well, if you don't use chemical energy, you could try mechanical energy. Well, what's mechanical energy? Well, you could EDM, plunge EDM around it, right? Electrical discharge machine, and you basically could machine the part. I mean, I don't know what their geometries are. They may have something that's not really practical to do. Or if they want to do it, it may be that when they make them originally, they need to put a barrier layer in there. I mean, if I really don't want to form a transit liquid phase diffusion bond because I want to unsolder it at some other time or unbraze it, let's say I've got nickel. And let's say I've got, well, I don't know exactly what I might put in here, but if I put a barrier layer, I know actually, let me give you the example. In superconductors, we have, in superconducting wires, we have copper, which is used in the wire to give thermal stability, and you have niobium and tin. Niobium-310 tin is one of the old-fashioned superconductors, not the ceramics. This is one of the ones that actually works, okay? They actually make magnets out of this, as opposed to the new high-temperature superconductors. And if you put that with the copper, the tin would diffuse into the copper, and you would run into problems because you'd lose your tin and you wouldn't have your superconducting properties. And you can't make this a copper tin alloy because then it loses its good thermal conductivity, which is why you had it here. So what they started doing 30 years ago was, in fact, this was, as my thesis advisor tells it, this was his idea, was they put tantalum in between. And tantalum forms a tantalum-310 intermetallic that stops the diffusion of tin into the copper. So you can put barrier layers in there. In fact, somewhere in here, see if I can remember which one of these guys, wonder if no, it's not this one. I was looking through these soldering books this morning. See, you were just waking up this morning. I was looking at soldering. Okay. No, I didn't mark it. But anyway, one of these guys had something in there about different barrier layers, which was essentially what this was all about. This is I've got 3 TLP joints here that one of my students made back 10 years ago for part of his doctoral thesis. This one is unusual in the sense that it's copper to copper, and we actually wanted to develop a way to bond copper bus bar, okay, without heating everything up, and copper bus bar for big currents. This was over at the National Magnet Laboratory. Actually, this was for the fusion reactor experiment that they were running over there. They wanted a simple way to bond bus bar, and well, one of the things you could do is you could plate the whole thing with silver. And silver and copper form a eutectic, and you can make a nice little braze joint. Well, we wanted something that would fill a gap, and so we started putting copper powders in with silver powders and melting the two. Or actually, we typically would, you need to fill a gap, and what we had was some copper. We put a piece of silver foil in there, we'd put some copper powder in here, and then we would put another silver foil, and then copper. So you have the two pieces of copper you want to bond. You put some copper powder in here to fill the gap, and you put the silver in. We figured we just infiltrate the copper powder with the silver. Well, it turns out you couldn't infiltrate it very far, because what happens is the silver starts to react with the copper and melts it. And those big copper balls, if you will, I mean, they're not very big. They're actually about half a human hair in size, but they get even smaller. And they actually start plugging up the interstices between the ones beneath it. And you actually can't you can't infiltrate with liquid. If the liquid, like in this case silver, will erode the copper when it starts to melt, you can't infiltrate more than 3 or 4 or 5 powder layers deep from either side, which means you couldn't form a joint more than about 0.010 of an inch thick. But this one actually is well over a centimeter thick, and what we did is we took the copper powders and we plated them with nickel. So these powders had a, gotta make it yellow, we plated them with nickel, and nickel will not dissolve silver. Nickel and silver are immiscible in both the liquid and solid state. And so now I have silver infiltrating nickel, which it doesn't erode, it doesn't alloy with. And because of that, I can get very deep infiltration of the silver. However, if I hold it at temperature, the nickel and the copper actually the nickel will diffuse into the copper, but it takes a little bit longer time. It's not liquid erosion, it's solid state diffusion. So over a couple of minutes, the thin nickel layer dissolves into the copper. Now the silver reacts with the copper and makes a TLP bond. So this whole thing, and the student machined it so you can actually see that it's a homogeneous solid joint. So we actually made, that's probably the thickest TLP joint, the thickest one I've ever seen, by far. But you had to do something to stop the diffusion initially, or slow down the diffusion initially. So that's the trick on that one. People actually do that. I showed the turbine blades, and they start with a paste, and they mix it together. But when you do that, the paste can't be very thick because you have the same problem of everything tends to form up. But if you infiltrate like this, you can get a thicker joint. This happens to be a piece, this is Inconel. So this is a nickel-based alloy that was TLP bonded, also fairly thick. You can see that, I mean, the student was doing tensile tests, and he just gave me some of the tensile specimens he didn't pull. And this one, pardon me? Inconel is nickel iron chrome. So if you want to think of it, Monels are copper nickels, okay, or nickel coppers actually. If you're on the copper-rich side of a nickel-copper phase diagram, you call them cupronickel, which the Navy uses a lot of. And then if you're on the nickel-rich side, you call them Monels. If they are nickel, iron, chrome, you call them Inconels. And the Inconels are basically similar to stainless steel, except you're nickel-rich rather than iron-rich. Okay, so if you're thinking, but they got both Inconels and stainless steels both have chrome in them. And this is a titanium, similar to a TLP type joint. Again, thick. You can see the region there. So if you're clever about how you do this, you can infiltrate, and you can make something of some thickness to make bulk materials. At one time, I wanted to make rapid prototype parts that way. But yep. Yep. The nickel layer here is probably only 5 to 10 microns. So the powder is probably 40 to 60 microns, and you got a 5 micron coating on it. So it's 10% of the diameter of the powder, approximately. And this silver might be 50 microns, and you're going to infiltrate. Actually, the silver depends on how thick of a layer you want to infiltrate. You can make it 20 thousandths or 30 thousandths, so far as that goes. If you want to make it much thicker, it might be that you want to put another layer of silver in between and have it infiltrate from a number of different directions. Or another thing is you could add silver powders to the whole thing and just help it, you know, kind of pre-infiltrate it with solids, if you will. You have to have a little bit of pressure on that to get rid of the porosity and stuff. Here, for TLP, well, it is TLP, but the copper silver eutectic, if I remember, is about 7, I think it's 723C. So you might bond this at 800C or something. I mean, the silver melts at 963, I think is the melting point of silver, and 1083 is copper. And the eutectic is something like 723. So the actual processing temperature might be 800. Actually, the student gave me these handy dandy little things. 850 was his joining temperature, the one that I'm panning around. And it was copper, 10 silver, 6 nickel. So I told you it was 10%. He said 6%. Okay. I mean, yeah, I was just giving you a kind of typical thing. Okay. And the joining time, holding time was 30 minutes to form that TLP joint. Okay. So you made the whole joint in 30 minutes. And he doesn't say what kind of powder or pressure, but I know the braising furnace he put it in was just kind of a spring force. I mean, it was just a light spring. It wasn't, we didn't have a big heavy press to do hundreds of PSI. It had only a couple of tens of PSI. Okay. Told enough stories today that we're not going to get to soldering, so let me tell you about activated diffusion bonding, which will finish up diffusion bonding. I actually did want to tell you those other stories about some of these things because they illustrate some of the principles. And it turns out people do a lot more transient liquid phase diffusion bonding than they know about. Okay, most of the time they don't even know they're doing it. But I call it activated diffusion bonding. But you have to be careful because Pratt & Whitney came in and started selling people on this idea of transient liquid phase as their trademark. General Electric came in and started calling their process, which was the exact same TLP process, they started calling theirs activated diffusion bonding. But what I call activated diffusion bonding is where I change the surface of the material. There are times when I have a material that is in this case is iron, the example I'm going to give you. Iron is the material, and I want to bond that at very, very low temperatures. Well, it turns out O'Brien, Rice, and Olson, this is January 1976, Welding Journal. They were actually trying to make very low temperature joints when this was Rocky Flats, where they used to make the nuclear weapons and stuff. And there were certain times in nuclear weapons where you don't want to heat things up too much when you're assembling them. And they wanted to join two pieces of high strength steel. It turns out this was marging steel, so these were like 220 KSI steel. And they didn't want to go above 200 degrees centigrade, if I remember. Well, that's way below 6/10 of the absolute melting point. And what they ended up doing, yeah, it was 200 degrees centigrade. Wait, sorry, take it back. Okay, yeah, okay. Well, 200 to 400. Let me just say it's 200 to 400. You can go back and read the paper. They ended up plating this with silver. And they ended up using 20 KSI, 20,000 PSI at 200 to 400 degrees centigrade. And they ended up getting joints that had 100 KSI tensile strength. Now the base material, the base iron, had about 220 KSI. And there's another phenomenon going on here called contact strengthening, which we're going to talk about when we get to braising. But nonetheless, iron is a problem because it forms at 400 degrees C. The iron oxide is so stable, you're not going to diffuse it away. You might be able to flux it away. Silver, on the other hand, forms an oxide, but the oxide in a vacuum will decompose at 400 degrees C. So you can evaporate away the surface contamination. And now, typically I told you diffusion bonding was done at 5,000 psi. Well, they kind of goosed it up a little bit to get more asperity collapse. Silver is nice and soft compared to the iron, which had tremendous strength. The silver flow stress is about 10 ksi if this is nice pure silver. So I'm pressing down with 20,000 psi on a material, a soft material at the inner layer that only has 10,000 psi strength. And remember, the compression pressure for a hardness test is 3 to 1, right? The indentation pressure for a hardness test is about 3 times the compressive yield stress of the material. So they're getting up to where they're almost forcing the silver out of this joint, pressing it very hard, getting a lot of contact area, driving off the oxides with temperature, but they've changed the surface. They've activated the surface, which is why I call it activated diffusion bonding. They activated the surface. The iron surface isn't going to bond at these temperatures, but a silver surface will. So you change the surface. Now that principle is a worthwhile principle in lots of cases. I had a situation where someone was trying to braise to hafnium. Well, why would someone want to braise hafnium? Hafnium is a refractory metal. It turns out, if you've ever seen air-operated plasma cutting torches, turns out the little electrode in there is hafnium. Okay, we can talk about it later about why you want to use hafnium as the electrode, but it turns out hafnium oxide, which will form when you make this air-operated plasma torch to cut a piece of metal, you're just using compressed air. The air is going to oxidize the surface of the hafnium, forms hafnium nitride, hafnium oxide, but that material has a little bit of electrical conductivity, and you actually can still get a current through there to run your plasma arc. And so they tend to use hafnium, but they were grabbing the hafnium and putting the current through it by just putting it in a copper sleeve. The problem is, everything would get so hot, the copper would, and the thermal expansion problems, the sleeve would lose its strength as the copper would creep. And so they wanted to make a good braze joint, and they tried everything to braze hafnium to copper. Well, in this case, the hafnium had such a tenacious oxide, there was nothing that really ate it up that wouldn't just destroy the copper, okay, in terms of a flux or something. So I said, well, why don't you just nickel plate the hafnium? And now you're bonding copper to nickel, and there's lots of braze alloys that you can use for bonding copper to nickel. And it worked out just great, okay? So people come to me all the time and they say, well, we can't bond such and such. And I would say that a certain fraction of the time, 20 to 30% of the time, I say, well, why don't you just plate the surface with something else that is easy to bond to? But you have to understand, whether it's a contamination problem or a surface roughness problem, whether plating the surface, and then you got to figure out what it is you're going to plate with. So you have to understand a little bit of metallurgy to do all that, okay? But activated diffusion bonding, here's an example of squeezing this together, having very thin silver layers, and you can say, well, if I got a silver layer that only has 10 ksi strength, how do I get 100 ksi in the joint? Well, that's contact strengthening, and we're going to get to that when we do the braising stuff, and I'll talk about contact strengthening there. But the point is, they made a diffusion bond and bonded 2 pieces of iron together using silver, and the silver melts at 960 degrees centigrade, and the iron melts at 1500 degrees centigrade, but they actually made the joint at 400 degrees centigrade, below this 0.6 of the absolute melting point that I told you about. Why? Because they used even higher pressures, and they used a metal that evaporates away its oxide at low temperatures. So you can do it with gold, you can do it with platinum, you can do it with a number of things. Platinum actually is kind of interesting because platinum will dissolve carbon quite readily. You can dissolve like 6% carbon in platinum. And as a result, you can have contamination on the surface. You can have organic contamination on the surface. Platinum also doesn't form an oxide. So platinum's kind of interesting in the sense that it will dissolve away some of the carbon contamination, and not everything will do that. Okay, iron will, and some other things will. Nickel won't, but anyway. So you have to understand some of the metallurgy on how to get rid of these surface contaminants. Okay, so I'll talk to you tomorrow, and we'll start talking about soldering tomorrow.